Okay, start. This is the last class for. This is the last class for module 3. The last class for module 3 on stability. So far we have discussed how many types of stability? 3 types. One is steady state, transient, and dynamic. Dynamic is mostly an old one, no longer used, but it was a type of stability. It's faster AGC, diabatic stability is no more required. Okay. So when we say transient stability, we have discussed when we say transient stability. What exactly we mean? You mean the variation of rotor angle with respect to time, right? And this can be obtained by two means. One is equilibrium criteria, which gives a qualitative measure for power system stability, transient stability, and the other one is solution to the swing equation. The other one is solution to swing equation. Okay. So that is what we will do. Swing equation requires numerical solution because on the left side we have this square delta by dt square is equal to Pm minus Pe, the accelerating power, which is proportional to sine delta. So we have delta occurring on both sides. We have delta occurring on both sides, and we have a sine term also. Because of this, this is a nonlinear equation, and we can only solve it by iterative methods. We take initial case, okay, and then iterative, right? So there are several established methods for solution of the swing equation. So for you, we will discuss on the simplest one, known as the point-by-point method of solution or step-by-step method of solution. Okay. The closed form of solution for the swing equation is not possible. What is a closed form? It's like you integrate something, you get some result. That is known as closed form. So for swing equation, it's not possible. So in a multi-machine system, it has to be solved for each machine by means of numerical method. Even in single machine infinite bar system, we have to resort to numerical technique. So what is to obtain variation of delta with time and determination of critical clearing time. Okay. So especially we have four methods: point by point, modified Euler method, Ramsey-Coulomb method, Miller's method. This is the most widely used for researchers. Ramsey-Coulomb method, you might have heard it. It's a numerical method, but point by point method is the simplest one to show you how the swing equation is solved. Okay. Write down all four. You write down names of the four methods. You write down. Okay. Point by point method, modified Euler method, Ramsey-Coulomb method, and Miller's method. Okay. Okay. So what is this point by point method of the solution? So it simply says that the exam, the question that will be of the form, describe point by point method of solution to the swing equation. That's it. Okay. It will be a theoretical question. No problems. May not be asked. But our objective here is that this is the swing equation. Write down the swing equation, and we write it in this form: d square delta by dt square is equal to dA by L. dA by L. Okay. And this solution is obtained in discrete intervals. We take a small step size, right? Say 0.01 second. We will take a small step size. That is what how we are going to solve. Now, why this integration is not possible? Because this accelerating power changes. Because the accelerating power changes from every step. So, for this rocket, mechanical power input, electrical power output changes at every step. So, therefore, this acceleration is not constant, and hence you cannot integrate. Therefore, you need to integrate only for a small duration on which you can assume the accelerating power to be constant, right? So, that is the principle behind it. So, when you write the answer to this question, you write in the first swing equation. Then you write that for small intervals, the power is not constant. Therefore, we separate it into several discrete intervals. The acceleration is calculated at the beginning of an interval and is assumed to constant from the middle of the preceding interval to the middle of the current interval. Now you will ask why middle, why not end? This is the procedure, one defined procedure. If you go to Range-Kutta method, it's a different one. Okay, it's just one of the procedures. Now speed deviation is assumed constant for the whole interval, speed deviation. Okay. Then every interval you assume a particular accelerating power and the speed deviation. That's it. Okay, that is the principle behind this. Okay. For example, it is shown here in mathematical form. So therefore, the change in speed is equal to delta t into acceleration, which is from the middle of the previous interval to the current interval, which becomes this. You see, the acceleration we are taking for the previous interval, which is assumed to be constant from the middle of the previous interval to the current interval. Into time, acceleration into time is speed. That is acceleration into time is speed, right? dv by dt is a. So d omega by dt is alpha. Okay. So this is that speed. And we find out the variation of delta from this speed deviation. Okay. So you can say that find the speed deviation, find speed deviation, compute angle deviation from this speed deviation. So that is what you have done. And what is the difference here? The difference is that you do it for a small interval delta t. Because we are considering the acceleration to be constant over that small. That is the whole process. So directly go to the question. This I have given you as part of the assignment. So this is the question. Okay. Write down the terms, various parameters. 20 MVA, 50 Hz synchronous generator. First line in 20 MVA. This is the problem that you are solving in your lab. Okay, where you are writing a code, Scilab code. You are running a Scilab strategy. Okay. So 50 MVA. 50 Hz synchronous generator, 20 MVA. 18 megawatt power is delivered. Second line delivers 18 megawatt power. Okay, first is 20 MVA 50 Hz generator delivers 18 megawatt power. Okay, over a double circuit line to an infinite bus. The double circuit line. You can draw a double circuit line. So third point. I would say point number 1. Point number 2, point number 3 is double circuit line. Okay. Generator has a kinetic energy of 2.52 megajoule per MVA. transient reactance is 0.35 per unit. Add it here. Point number 1. Transient reactance is 0.35 per unit. Each transmission circuit has resistance 0 and a reactance of 0.2 per unit. 0.2 per unit. Okay. All this is point number 5, transmission line parameter. Okay. Then E dash and generator terminal voltage. Generator voltage is 1.1 per unit. Bus voltage 1.2. Then this is 1.1 per unit here for the generator, and bus voltage is 1.0 per unit. Okay. The three-phase fault occurs at the middle of one of the transmission lines. Somewhere here the fault occurs. Okay. That condition we have discussed in equivalent diagram. What happens? Okay. Now we are directly going to obtain the solution. Now it says any code write a program to obtain the swing curve. Okay. So point number 5 is 6 is this voltages, and you need to obtain this swing curve. Swing curve means what? At least remember this swing curve is delta versus T. Right? That is the swing curve. Under 3 conditions. One is the fault is cleared. Cleared means line का टुकड़ा disconnect कर दो. In 2.5 seconds. It cleared after some time. 6.25 seconds. And finally it is not cleared. Okay, it's not cleared at all. So what happens to the delta T curve? So will you write the question? Don't write the whole question, just write this parameter so that when you solve it, you can refer to that. Write the parameters. Okay? Write the parameters. Hello? Now directly I go to the end, the solution. This is the curve you might have obtained in your lab. Right? You have obtained this curve by running. If you run that Scilab code, you will get this curve. So this is the solution to 3 conditions. Okay? Fault cleared within 2.5 cycles, 6.25 cycles, and sustained fault. So if the all of you must have put it in your file, lab file. So sustained fault means, see, the generator angle goes on increase. That means the unstable condition. When it is only 2.5 cycles, it is clear. If you see, it's for the swing one. See, the deviation of delta is not much. Okay, it increases and further then reduces. That means the system is stable. For 6.25 cycles, it is still stable, but the expression is higher. The expression of delta is higher. Torque angle delta in degrees is higher in that case. The fault is clear delta. That means critical clearing angle is much beyond that. Okay. Now we will see the results. The results. So these, when you see the Scilab, the prompt, okay, command line prompt. So when you run don't run the code on the command line directly. Save it as a file, put it in some workspace. Workspace means any folder you create, okay, and inside that you put the file, run it. So that command line is free for you to see the result. So if you run that way, you will see all these excursions in the command line. Okay. So what you see here, you see you will start with 2.5 seconds. Okay. This is plotted from the program itself. So if you want, you can go through the program and find out how it is plotted. Okay. So what is the step size? What is the step size? Step size is the delta T note by delta T. 0.05 second. That's the step size. 0.05, 1, 0.15, 0.20, 0.25. Okay. So you see here 21 degree, 24, 29, 34, 36, 33 here. Right? So it goes up to maximum 33.97 degrees. Okay. We discussed about it going beyond 90, then coming back. It is not that way. It's just going up to 33. And after that it is reducing. Therefore, the system is stable. Okay.
So maximum 36.690.
Okay, 36. Yes, yes. Right, right. It is maximum is 36.6. That is the peak. See, thereafter it is over. One of the note it down. 36.69 degrees. That is the maximum if the fault is cleared in 2.5 seconds. 2.7 get a second. 1 cycle is how much a second? 1 cycle means 1 cycle how many seconds?
20 milliseconds.
20 milliseconds. Is it? So 2.5 cycles is 100 milliseconds. Is it? Or 50? 50 milliseconds. Right? So that means the fault is cleared in 50 milliseconds. Right? Fault is cleared in 50 milliseconds. 50 milliseconds. Remember, just count 1 second, then imagine what is 15 milliseconds. So that means before that the circuit breaker must operate. It's not a critical one, but it is in milliseconds. Now we go to the next one. 6.25 seconds. So what is the maximum one? I think 51.6. Right? After that, total leakage. Right? Right? Okay. Now we go to the next one, sustained fault. Here you see there is a problem. What is happening? You see the angle goes up to even 159 degrees, much lower, near to 180 degrees. Goes into this. So that means there is unstable scenario. Before this, the generator must have been disengaged. Okay. Now we move back. So how this thing is plotted? So you can take at your print in the lab if you have done it. Otherwise, you can see the code. From there, you can see how this curve is plotted. Okay. Then we see the solution. First is you have written the question. Our objective is to obtain the swing equation, right? We are plotting the swing equation, isn't it? We are plotting the swing equation for discrete intervals, small interval. And what is the interval in this case? What is the interval in this case? Just say 0.05 seconds. Okay, for that interval we are plotting. So we start with calculating m. H value is given. Okay. And this is the power before the fault, pre-fault. So we are discussing pre-fault first. Okay. Pre-fault power is 0.9 per unit, and we calculated pre-fault is 21.64 degrees. Okay. Write it down. Okay. This here any doubt? For even power transfer, and we start with delta results. This is our point. Then next, during fault. This is the fault is in the mid of the line. Mid of the line is connection to ground, right? Mid of the line is connection. So this line is having a reactance of 0.2. So if you assume the reactance to be uniformly distributed, then we have on two sides 0.1 reactance. Okay. Terminal voltage, generator voltage. This is the generator reactance or generator plus transformer. You know how to calculate the total one? This plus 0.35 into 0.01. These two are in parallel. Right? Is it? 0.2 into 0.1. 0.35 into. You have to obtain the Thevenin reactance in this case. What is the total reactance of the line now? Check this. how you obtain the reactance under this condition from network theory. Network theory application, how you obtain the reactance. We get 1.25 per unit. Now what is the power transfer during fault? Say, when we discuss equilibrium battery, we discuss that if the fault is at the generator end, then power becomes zero during fault because it is at the generator end. Power goes to the ground. But if it is at the middle of the line, some power flows in the line till it reaches the fault location. And because of which we have got this much power going in the line. Okay, based on this reactance diagram. Write out this. Second, during fault, just write down power transfer is 0.88 sin delta. During fault, the power transfer is 0.88 sin delta. During fault. Post fault. Now our objective is computing the delta versus time curve post fault after the fault. Now what is the total reactance? 0.35 plus only the upper part of the line because the lower arm will be disconnected after the circuit breaker operation. So total reactance is 0.5 and hence the power transfer post fault is 2.0 sin delta. And we have chosen the interval to be 0.05 seconds. Okay. And from the swing equation, see this is swing equation. We discussed that we will take the accelerating power to be that of the previous interval. That is equal to the mechanical power input minus the electrical power output during the previous interval, delta n minus 1. What is delta n minus 1? Delta 0 for the first case. Delta 0 was 21, something like 21.7. Okay. Then we will calculate the increase in delta from this equation, okay, which is equal to the delta in the previous interval. It should be delta plus this from the we get from the swing equation. Okay. And then finally we obtain delta. Now if you look at the code of the Scilab code, has implemented this code. Okay, this principle or this formula has been implemented in the Scilab code to plot the curves. Okay, and go and cross check it. Okay. And then we calculate the various accelerating power. Initially, P0 minus no power is transferred before the accelerating power means there is no fault. Normal situation, P0 minus means normal situation. No accelerating power. All the power that is mechanical input is going to the electrical output. Okay. But during fault, 0 plus and 0 plus the fault occurs. Because of which this is the power transfer. You have just written 0.88 sin of delta 0. That is the power transfer. And hence the accelerating power is Pn is 0.9 per unit. It's given. We computed here. Pre-fault power transfer 0.99. But because of the fault, it is reduced. The electrical output is reduced 0.88 sin delta 0. And this is the accelerating power. Okay. So we take the average acceleration from the previous interval and the current interval divided by 2. So this is the accelerating power. So with this, we go on computing the delta and plot. So this is, nobody will ask you at undergraduate level, we don't ask such type of problems to be solved because it has to be solved programmatically only. So your job is to look at the program in your lab and see how it has been implemented in Scilab. Okay, the code is with you. Okay. And finally, we discuss how to extrapolate this concept to large system. When you say large system, we talk about various generators. Just like in your lab code, if you have downloaded Mat Power, you might have seen case 30, case 14, case 30, even 3000, 6000 bus systems are also there. Okay. So if you want to do load flow for a 30 bus system, what information you need? If you want to do load flow, so what information you need? First is the load requirement at the different bus. In a 30 bus system, which is a standard system, so all the 30 buses the load will be given. And in that system, I think there are 41 transmission lines. So you need R and X for the transmission lines. Otherwise, how you create the Y bus? Right? So if you see the mat power, you might have downloaded the mat power. Okay, that video I have created for this experiment. There I have mentioned how to download mat power and how to install or put that in the MATLAB workspace. Or Octave, it also runs in Octave. So if you go inside that folder, you will find various case files. It will be written like case 30, case 57, case 118. Just double click on that. It's a node. Okay, .m file. So there you will find all the information, bus information, line information. All these things is required for doing load flow. For economic dispatch, you need the generator cost function, quadratic cost function. Then only you can do economic dispatch, right? Or optimal power flow. This information is available in that case file. My question is, can you do, those are the two modules, right? Module 1 load flow, module 2 is economic dispatch. Can you do stability analysis for that 30 bus system, which is a large scale system, using that case file? Is it possible? Is it possible? Mat power case file नहीं कर पारी हो? और what extra you need? So it is how they get transmission line data into Rx value, generator cost function, quadratic function, AI, DI, CI, all values will be given. Okay. Go. What information you need to perform this kind of study? Generator inertia constant, right? That is the only information that you need to perform the stability study. Regarding the generator parameter, generator inertia constant. So suppose you go and do PhD in stability area, any kind of system, you need generator inertia constant. Okay. So how we proceed? First thing is that we should proceed do a static load flow model based on the Y bus, and for Y bus you need line parameters R and X, which are given in those mat power case file. Perform power flow computation based on the above model. This is the P fault position delta 0 and megawatt output PG of all of them. Then construct the dynamic model for each turbine generator, which is a second order swing equation model. Okay. ALS area, which are part of module 5, which are generally management. Selection of a fault contingency, cognitive and stability must be investigated. Apply the fault at T equals 0. Select a fault. Which line you are going to get a fault on. Okay. Then integrate the swing equations for this system by using mostly longitudinal CFK for different time intervals and plot the angular equations. Okay. Then perform power flow computation to find the minimum answer. So there can be a long question, 4-mark question, which will be asked. What are the various steps to perform stability analysis for a large scale system? In that case, you will write this. Okay. So this completes module 3. Post midterm, we will move to module 4. Stop.